So far we've only mentioned magnetic fields that come from permanent magnets. But it would certainly be much more useful if we could create magnetic fields that we could vary, make stronger, make weaker, switch on, switch off. Well, fortunately in our universe there's another way of making magnetic fields. It turns out that electric currents already have a magnetic field associated with them. One way to verify this is to find a wire with some current running through it and hold a standard magnetic compass near the wire. You'll see the needle will be deflected by the magnetic field associated with the current in the wire. In fact, if you do some really careful experiments, as were done many, many years ago, you'll be able to map out the exact shape of that magnetic field. If we look now at a current moving along in some direction here, I, what you would find is a magnetic field that circulates, concentric circles of magnetic field around that current carrying wire. Now what direction do they go? Well, again we need a right-hand rule here. It's slightly different to the last one. We take our right hand again and we point our thumb again in the direction that positive charge is flowing, in the direction of current. So I'll make my thumb point off in that direction, and now my fingers on my right hand, they curl around in the direction that the magnetic field is circulating. If the current was to go in the opposite direction, then my fingers would curl again in the opposite direction. That tells us the direction the magnetic field is moving. And you can see in the diagram, that's exactly the direction that we have for those green magnetic field lines. Now, what if we have two current carrying wires next to each other? Well, each of those will have a magnetic field associated with them, and the current from one wire will move through the magnetic field of the other. In the diagram here, we have two current carrying wires moving into the screen. Again, we have to have a direction usually that goes into the screen. In this case, the current is moving into the screen. And we can see what the direction of the magnetic field will be from that leftmost current carrying wire. It's going to be concentric circles, as we saw before. And again, using our right-hand rule, we can figure out what direction those circles are moving in for the magnetic field lines. Now, the current carrying wire on the right-hand side now has a current moving in a magnetic field. We can use our first right-hand rule, remember thumb, fingers and palm, to find the direction of the force. And again, good practice, if you do it properly, you'll find that this right-hand side wire has a force pushing it in that direction. That's the force from the magnetic field of the left wire onto the current in the right wire. And we could do exactly the same analysis by considering the magnetic field from the right wire exerting a force on the current in the left wire. And you'd find the force on that left wire is towards the current on the right. In fact, two current carrying wires with current in the same direction have an attractive force between them. And if you turned one of those currents around, and it's a good practice to try and do this calculation, you'll now find current carrying wires with opposite directed currents actually have a repulsive force between them. Again, in many instances, this is a useful force to tap into. Now, what if we take our current carrying wire and manipulate it into some different shape? We have a lot of options here to make different forms of magnetic fields. One fairly simple one is to make our current carrying wire into a single loop. And you can see a loop here carrying current. The loop, it's kind of ambiguous to know which direction is which. I'm going to say that the current carrying wire has the current moving off to the right in the front of the screen and off to the left in the back of the screen. You'll see in a minute what direction it must be by the magnetic field lines I'm going to draw. Let's go over to the left-hand side and think about the magnetic field from this wire over here that has actually got current coming out of the screen. By our right-hand rule, this must have a magnetic field that goes around in this direction as shown. And of course, a bit further out, the field is a bit weaker. It will be going around with a more widely spaced thing. And a bit further out, we might not be able to draw it here, but we can imagine it's going to leave at the top and arrive back in here at the bottom. Now over on the right-hand side, where the current is going into the screen, we're going to have a magnetic field going in a similar fashion using our right-hand rule, this time going around in this direction. And a bit further in, we'll find a slightly weaker field moving around in this direction. And then further out again, maybe a magnetic field leaving like that and arriving back in like this. And you can see by the symmetry in the center of this ring, there must be a magnetic field in that direction and one arriving from below in that direction. So a simple loop gives us a reasonably complicated magnetic field structure. You can already see it looks a little bit like a bar magnet in that there are magnetic field lines leaving from the top and arriving at the bottom, as if the top was kind of like a north pole and the bottom was kind of like a south pole. In fact, we can make it even look more like that if instead of a single loop, we do a whole lot of loops into a coil that we sometimes call a solenoid. In a solenoid, we have current going around many, many loops, all closely spaced together. As you can see in the diagram there, it's fairly straightforward to make a nice uniform coil of wire, and when current runs through that, you can see in the bottom diagram there, where now current into and out of the screen is either a dot or an X. You can see the magnetic field lines along the centre of that solenoid are really close together. That's a strong magnetic field. The magnetic fields leave one end and enter the other, and indeed this looks very much like a bar magnet. This is an example of an electromagnet, it's sometimes called, and this is a device you can switch on, you can switch off, you can make a large current to get a large field, a small current to get a small field. What we're going to see in the next topic is, instead of taking magnetic fields arising from currents, let's see if we can't produce a current using a magnetic field.